The paper is about making contextual bandit systems keep working when the world changes. A contextual bandit is a setup where, at each step, you observe a context like a user profile, a agent state, or sensor readings. You pick one action from several choices, and you receive a reward. In a stationary world, the bandit can gradually learn which actions work best for which context and minimize regret, meaning it performs close to the best possible strategy. But real deployments rarely stay stationary. The distribution of contexts can shift because users change, seasons change, devices change, or data pipelines drift, and suddenly the assumptions that made the bandit reliable no longer hold. The authors treat these changes as domain shifts across multiple domains over time, including both abrupt switches and gradual drift, and they propose a domain adaptation approach that does not require knowing when the domain changed. Their core idea is to learn a robust representation of context in a self-supervised way using unlabeled data, then feed that representation into standard bandit algorithms, so the online learner adapts faster and suffers less regret when the environment shifts. To position the idea, they connect 3 research threads. First, classic contextual bandits like LinUCB and Thompson sampling assume a fairly stable relationship between context and reward and are widely used in personalization. Second, non-stationary bandit work tries to cope with change using heuristics like sliding windows, resets, or weighted updates, but often does not explicitly learn transferable features that remain useful across domains. Third, representation learning for bandits suggests that unsupervised or self-supervised features can make online learning more sample efficient and more robust to distribution changes. The paper also clarifies what it means by abrupt versus gradual shift. Abrupt means the context distribution changes sharply in a short moment, while gradual means the same overall change accumulates slowly across many steps. They measure performance with cumulative reward, the total payoff collected, and normalized cumulative regret, which compares the bandit's reward to an oracle that always picks the best arm in hindsight, an optimistic ceiling used to show how much room remains for improvement rather than a deployable method. Methodologically, the contribution is a 2-stage pipeline. First, in an offline pretraining stage, they learn an embedding function that compresses raw context vectors into a lower dimensional representation that is intended to be more domain invariant, or at least more stable under shift. They consider several self-supervised options: a NOR baseline that uses raw context directly, a vanilla autoencoder that trains an encoder, decoder to reconstruct the input so the encoder learns a compact summary, a masked autoencoder variant that randomly zeroes out parts of the context during training and forces reconstruction, encouraging robustness to missing or altered features, and a toy contrastive method that creates 2 noisy augmented views of the same context and trains the encoder to map them close together while pushing different samples apart, aiming to capture invariances that resemble domain perturbations. After pretraining, they freeze the encoder and move to the online stage. Each incoming context from the evolving domains is embedded through the fixed encoder, and then a bandit policy learns on top of that embedding. They plug the representation into multiple bandit families, including epsilon greedy, LinUCB, with confidence bonuses, Thompson sampling with A's, posterior sampling, and neural variants where a small network predicts rewards and uncertainty is approximated with techniques like dropout or noise. In experiments, they run through 8 domains labeled A through H with designed shifts in the context distribution, including both abrupt transitions and gradual drifts, and compare combinations of bandit algorithms with the different representations. The main takeaway is that using learned representations, especially contrastive and standard autoencoder embeddings, typically reduces cumulative regret. and increases cumulative reward compared with using raw features, meaning the bandit adapts faster after shifts and ends, up closer to the oracle ceiling. Some neural methods can reach high reward, but may show higher variance and require careful tuning early on, while representation-based approaches tend to give a more reliable improvement across settings. The conclusion is that a simple offline to online strategy, pretrain a compact self-supervised encoder on unlabeled contexts, freeze it, and run classical or neural bandits on the embedding, can make contextual bandits more robust to non-stationarity, and the authors suggest future directions like continual learning of representations and more domain-aware contrastive augmentations to handle even richer real-world shifts.